Hello everyone, I'm Professor Xiaonan Gao. Welcome to the General Chemistry class. This session will continue with the basic concepts of chemical bonding chapter. The Lewis structure of water gives the impression that three atoms in water are arranged in a straight line. However, the experimental determined shape of molecule is not linear. The molecule is bent. Does it really matter that the molecule is bent rather than linear? The answer is yes. Decidedly yes. As we will learn in this chapter, the bent shape of water molecule helps to account for the fact that water is a liquid rather than a gas at room temperature. In chapter 13, we'll find that it is also accounts for the ability of liquid water to dissolve so many different substances. What we seek in this section is a simple model for predicting the approximate shape of a molecule. Unfortunately, Lewis theory tells us nothing but the shape of molecules, but it is an excellent place to begin. The next step is to use an idea based on the repulsions between the valence shell electron pairs. Valence shell electron pair repulsion model, abbreviated as VSEPR, predicts the geometry of molecules from an electrostatic repulsions between the electron pairs, either bonding and non-bonding electron pairs. Now let's see the VSEPR model one by one. First one, AB2 molecule. In this type of molecule, there are two atoms bonded to the central atom, but zero lone electron pairs on the central atom. In this regard, both arrangement of the electron pairs and the molecule geometry are linear. Take beryllium dichloride, for example. There are no lone electron pairs on beryllium, but only two single bonds with each chloride. The geometry is then linear. Next, for AB3 molecules, there are three atoms bonded to the central atom, but zero lone electron pairs on the central atom. In this regard, both the arrangement of the electron pairs and the molecule geometry are trigonal-planar, a 2D structure with a 120 bond angle in between. Take boron trifluoride, for example. There are no lone electron pairs on boron, but only three single bonds with each fluoride. The geometry is then trigonal-planar. Next, take AB4 molecules, for example. There are four atoms bonded to central atoms, but zero lone electron pairs on the central atom. In this regard, both the arrangement of electron pairs and molecule geometry are tetrahedral, a 3D structure with 109.5 degree bond angles each. The most famous example is methane. There are no lone electron pairs on carbon, but only four single bonds with each hydrogen. The geometry is then tetrahedral. Next, for AB5 molecules, there are five atoms bonded to the central atoms, but zero lone electron pairs on the central atom. In this regard, both the arrangement of the electron pairs and the molecule geometry are trigonal bipyramidal. Take phosphorus pentachloride, for example. There are no lone electron pairs on phosphor, but only five single bonds with each chloride. The geometry is then trigonal bipyramidal. Three chlorides equally lay on the planar with a 120 degree bond angle. The other two chlorides perpendicularly distributed on top and bottom of the plane with a 90 degree bond angle to the three chlorides. Overall, it is a trigonal bipyramidal structure. Next, for the AB6 molecules, there are six atoms bonded to the central atom, but zero lone electron pairs on the central atom. In this regard, both the arrangement of the electron pairs and the molecule geometry are octahedral. Take sulfur hexafluoride, for example. There are no lone electron pairs on sulfur, but only 6 single bonds on each fluoride. The geometry is then octahedral. 6 fluoride equally lay on the 3-dimensional directions with a 90-degree bond angle each, displaying an octahedral structure. All the 6 fluoride are in equal position. Here's a table summarizing the 5 arrangements of electrons, pair, and molecule geometry. Make sure to spend time after class and memorize all of them with their names, geometry, and details. When comparing bond angles of methane, ammonia, and water, which all possess a tetrahedral distribution of electron pairs, we found that the bond angles are different. Methane has the largest bond angle, then ammonia, water, has the smallest bond angles. This phenomenon is caused by the repulsion force between the lone pairs of electrons and bonding pairs of electrons. Generally, the lone pair versus lone pair repulsion is the largest, like in water. Second is the lone pair versus bonding pair repulsion, like the ammonia. And the least repulsion is a bonding pair versus bonding pair, like in methane. Knowing this repulsion differently, it will help us to further develop the VSEPR theory with central atoms having lone electron pairs. Similar to AB3, the AB2E also possesses a trigonal planar arrangement of electron pairs, but its molecule geometry is bent. Like sulfur dioxide, the lone electron pair forces the 2 oxides to bend over from a linear geometry. Similar to AB4, the AB3E also possesses a tetrahedral arrangement of electron pairs, but its molecule geometry is trigonal pyramidal, like ammonia. The lone electron pair forces the 3 hydrogen to move down the planar and form a trigonal pyramidal geometry at the end. Another similar structure to AB4 is AB2E2, with 2 lone pairs. Water is a typical example of this type. 2 lone pairs takes 2 corners of the tetrahedral arrangement, so the geometry is bent. And similar to AB5, the AB4E also possesses a trigonal bipyramidal arrangement of electron pairs, but its molecule geometry is distorted tetrahedral, like sulfur tetrafluoride. The lone pairs of electrons force the 4 chloride to move down the planar and form a distorted tetrahedral geometry at the end. Second similar structure to AB5 is AB3E2, with 2 lone electron pairs. And chlorine trifluoride is an example of this type. 2 lone pairs takes 2 corners of the trigonal planar arrangement, so the geometry looks like a T-shaped. Third similar structure to AB5 is AB2E3, with 3 lone electron pairs. And iodine 3 minus is an example of this type. 3 lone electron pairs takes 3 corners of the trigonal planar arrangement, leaving 2 iodines on top and bottom each. So the geometry is simply linear. Similar to AB6, the AB5E also possesses an octahedral arrangement of electron pairs, but its molecule geometry is square pyramidal, like the bromine pentafluoride. The bottom lone electron pair forces the 4 fluoride to move up the planar and form a square pyramidal geometry at the end. Another similar structure to AB6 is AB4E2, with 2 lone electron pairs. The 2 lone electron pairs sit up and down of the octahedral structure. leaving 4 fluorides on the plane, so the geometry is square planar. Here's a table summarizing all the 8 arrangement of electron pairs and molecule geometry. Make sure you also spend time after class and memorize top part of them, with their names, geometry, and details as well. Alright everyone, in this class we learned the Vespers theory, the arrangement of the electrons, and the geometry of the molecules. I hope you have enjoyed the class, and I'll see you next time.